repos, the Hugging Face data sets. We'll gather all that stuff up so you have a one-stop shop to refer to when you watch the playback. Now, a quick word about the meetup. If you're coming to us perhaps from Luma or LinkedIn or some other place where you may have seen the event advertised, this meetup is actually part of a much larger network of virtual and in-person groups. We hold multiple events per month, the idea being that we want to bring a diverse set of speakers that are working at the cutting edge of AI to our community. So we cover everything that you could imagine, from research to commercial applications to open source projects to interesting data sets. We try to cover it all. Now, this meetup is awesome because you're awesome. So if you are interested in speaking at an upcoming meetup, I highly encourage you to check out the link that I posted there in the chat, vox51.com/speak, to see what upcoming speaking opportunities there are that might be a good fit for your topic or research. Also, if your company is interested in sponsoring a meetup, we always love coming to new cities and checking out the local scene. So if you are interested in working with us to put together an in-person meetup in your city, do reach out. The best way to get that conversation started is probably on LinkedIn, and I've included my link to my LinkedIn profile there if you would like to start that conversation. Now, we do have to pay a few bills around here, so a quick word from our sponsor. Today's sponsor is Vox 51. If you're unfamiliar with Vox 51, it is the company behind the 51 open source computer vision project. It's an SDK, it's a UI, but what it allows you to do is to take complex data sets, visualize them. You can explore embeddings, you can annotate your samples, you can analyze and improve your models, you can do very advanced data curation tasks. It integrates with dozens of MLOps tools that you probably already use. It's open, it's extensible, and best of all, it's simple to install. Pip install is all it takes to get started. If you want to learn more, links are there in the chat. My colleague Eric is with us today, and he's going to give us a flash demo later on to show you some of the interesting things that have been developing on the 51 side. We'll wrap up our housekeeping items here with a few upcoming events. We've got some workshops that are happening in August. If you're interested in multimodal data, we've got a hands-on workshop that's happening on August 11th. If you're interested in the intersection of tool skills, MCP, and computer vision, my colleague is having a workshop on August 13th. And if you are interested in the curation aspects of computer vision, my colleague is also running a workshop on that topic. And I'll post the link there to the events calendar, which has all the workshops and the events there. Also, a final reminder, don't forget that our final day 3 of the series is happening tomorrow. So another exciting lineup of 4 great researchers. And then a final note on in-person events. So if you are in Chicago, Paris, Zurich, or London, over the next 2 weeks, we will be in these cities. If you'd like to join us at one of these events, do click on the events link that I posted there in the chat to register, as seats are limited for these events. And if you're local to these cities, we'd love to see you and meet you at one of these events. All right, that's enough out of me. So with that said, I think we are ready to go ahead and get started. If I look at my notes, our speaker order today, I believe is, I know we're battling some time zones here. Herman, Zhenjun, Jing, and then we will wrap things up with Ashes. So with that said, I'm going to go ahead and stop my share, which means that Herman, if you're with us, the floor is yours.
All right, let me quickly set everything up here that I can see you and I can see my slides. Thanks very much for the kind invitation. So today, what I brought essentially from ICRA here is a talk that I gave in the spatial AI and multimodal AI workshop at ICRA, and also covers a couple of things that we presented there in the main conference, as well as in a couple of workshops. And I put it all under the description of scene graphs in the future of mapping. By the way, if you can't hear me, just now is a good time to indicate. Otherwise, I'll just go ahead. Okay. So what do I want to talk about? essentially, there have been a couple of different developments in the last 2 to 3 years that are very exciting, and they shift a little bit the landscape of how at least I think about robot mapping in general. So maps, if we think about them as like a general tool that is available to robots, they essentially cover environment-specific information, such as the 3D geometry. If we run reconstruction, we may want to map different object instances, their locations. We need to maybe map free space and kind of different aspects of traversability. And we might also want to remember our past trajectories in these environments. Whereas other aspects of the mission that the robot then performs in these maps actually is environment unspecific, such as locomotion and control, image understanding, ego motion estimation, and so on. That is not really something that we have to keep in maps. Now, we have some interesting kind of new models that we can take as general priors and robots can just bring with them. And that, for example, is all the kind of common sense reasoning and semantic priors that LLMs, VLMs, and so on bring with us. But then on the other hand, as more and more robotics moves towards mobile manipulation and dynamic environments, there are a couple of additional aspects that we're interested in from our environments. So these are object dynamics, interaction experiences, functional connections. I'll get to that between, for example, light switches and lights, something that you can't really see. You have to gather from experience. And because it's so expensive to gather this information, you want to store it and keep kind of being able to retrieve it later on. And of course, then as we move into environments, something specific is then also user preferences as we, for example, move towards domestic service robots. Okay. And then kind of last 2 years, we now also have these very nice priors on monocular depth or sparse view geometry, models like VGGT, map anything, as well as we'll see, some kind of more generalizable navigation and manipulation skills, kind of models that really generalize well across environments, which, and this is my argument, while we have to change how we do mapping on robots, free up some of the space on this left side. So maybe we don't have to run geometry reconstruction from many different views over SLAM and bundle adjustment anymore, because at any point in time, if we have posed images, we can get very good dense geometry from these multi-view models. And the same that goes for free space and traversability. So there's 3 things that I want to talk about. The first is, what does it mean for SLAM and navigation if we, for example, don't remember reconstruction of our environments anymore? And then the second question is, if we don't need reconstruction, we want to build different kind of maps, how do they look like for applications in mobile manipulation? And I specifically advertise for this formulation of 3D scene graphs. And then I'll finally close with a little bit of an outlook on how we do mapping of physical properties and interactions. So to start with, the first question that we asked ourselves is, how can we do an entire SLAM pipeline without reconstruction at all? And our solution to that is called to go. So kind of PGO, bootstrap optimization, but just from 2 views. So we never actually have to triangulate anything. If you think about very regular SLAM, this is kind of how it looks like. You move a camera around in an environment. You kind of can measure some odometry, and then you can try to track or re-identify different landmarks that you see in this environment. And if you gather enough different views, you usually need at least 3, then you can triangulate their spatial position. And if you do this over time, you get a more and more accurate reconstruction of the environment. Now, if you only want to do this from 2 views, obviously you can't just triangulate, but there's a very kind of old concept actually. It started, I think, mostly with like LiDAR SLAM. People talked about pose SLAM. So in pose SLAM, we don't optimize over landmarks or something like this. We essentially still measure odometry, but then we get some kind of external hint that we might have seen something before, and we can essentially just connect 2 different viewpoints via loop closure edges. So kind of we notice these 2 cameras are looking at the same thing. We directly get a constraint between them. And of course, we can do stuff like this right now with models like Master, VGT, Map Anything. They exactly do this. Like we give them 2 views, and they can give us a metric relative pose between these 2 views. And that, of course, sparsifies the whole optimization problem of SLAM quite a lot. And we can build SLAM pipelines with that only do postgre optimization while still keeping very kind of dense geometric information for all of these different edges. And if we can if we optimize over that, we essentially get a much sparser problem. So how do we build these edges? There's essentially a couple of different variants that we look for. We could directly build them from Map Anything or a different metric reconstruction model. Most of them are actually not metric, but there are those and we can use them. What we find a bit more stable is that we still use kind of 2D, 3D correspondences out of these models and then run kind of PNP on top of that. It gives a little bit more robustness. And that means we can even take the more classic learned pipeline of 2D matches and lift them to 3D with something like metric 3D or something like this. So many different options that we can try. We can also, of course, always just get scale-free edges without doing any metric estimation. All of these are different ways how we can constrain two different views in our SLAM problem with each other. And then if you deploy this on very long trajectories, something like here, 5 kilometer, 10 kilometers, or something like this, we see that any kind of odometry source that we take as an input, we can actually get very high accuracy, even though we never do any bundle adjustment. And this accuracy, of course, comes from that we can do more loop closures than classical pipelines because models such as VGGT are really good at finding relative constraints between viewpoints that maybe don't have a lot of overlap. And then on the other hand, we get a lot of different edges that are still accurate enough to let us optimize. And we essentially gain very kind of accurate poses. So that means already for just pose estimation and SLAM, we don't necessarily need reconstruction. But then the second question is, usually we need some kind of traversability, free space estimation to move around in an environment. And so if we're moving around, again, if you ask this question, can we do it without any 3D reconstruction? Then one of the things that we looked at is, can we reason about movement from image space? And of course, you may be familiar with works such as vision language navigation that try to learn navigation from vision language models. This here is a little bit more of a kind of classical inspired approach, but I think it learns something quite valuable that we see is extremely useful later on. So what we try to do is we build on these classical approaches for exploration that would do 3D mapping and then frontier extraction, and you can kind of have a sparse set of frontiers. You can decide essentially where your robot should go next if it searches for something or tries to explore the environment. And we bring all of this to the image plane. So essentially we can gather with these 3D mapping approaches a lot of different training data, and then we can train to essentially just detect 3D frontiers from images. And then we can lift them later on, again, with some kind of depth model or a depth that we have available into 3D frontiers. Now, the advantage of this is we essentially learn how frontiers look like in images, but this network that we train here has not only the geometric information of the classical approaches, it can leverage all the visual context of these frontiers. So essentially what we do here is we also get the ground truth on how much would you be able to see if you go to that viewpoint. We can do that in simulation, of course, get a lot of training data from that, and now use the visual context to guess the information gain of each of these frontiers, something that geometric approaches were not able to do before. And from this, we can do these kind of votings and weight the different frontiers with each other. So this is how exploration then looks like in practice. You go somewhere, you see a viewpoint, you kind of lift these frontiers to 3D, and now we can always weight how long does it take to travel to a certain frontier versus what is the informativeness. You see that here kind of given with the size of the different frustums. And so we end up with a kind of very sparse navigation approach, can move around in the environment without actually requiring any reconstruction or actual 3D extraction of frontiers. All of this comes from single images. So how does navigation look like if you don't want to have any kind of reconstruction map at all? Well, we start out from a viewpoint, we maybe detect two frontiers, and we can simply travel to one of that. It's actually in view. So this is kind of just traveling inside what we anyway see. Then we might find a new frontier, we travel to that. Now we don't find any new frontier. That means we have kind of hit a dead end. But of course, we remember there was a viewpoint before from which there was some additional frontier visible. So we have not fully explored the environment. Now, in a general metric reconstruction, we would now directly select this as a target and do a planner to find a path over to that frontier. If we don't want to keep any reconstruction in memory because maybe we want to scale to a very large environment, then what we can still do is we can travel back our trajectory to that viewpoint from which we've seen that trajectory, and then we can go visit it. And this is essentially how this looks like here, without keeping any map, just kind of the map here is just for visualization purposes. And of course, you can deploy this easily also on real-world robots. All you need kind of is this network, and then it gives you some sparse 3D frontiers. Now, interestingly, the reconstruction that you see here on the top left is something, if you've ever worked with a spot robot, you know the depth camera in the hand is really low quality because it's for kind of close interaction. Now we just take the RGB camera, and this entire reconstruction that we built here kind of as a post-processing from the images that the robot takes is just made from feed-forward depth models. Okay, so what if you don't just want to explore? Again, there's a huge advantage of doing this entire navigation reasoning in image space, and that is that we can, of course, use these frontiers now and use any other kind of visual models to reason about the different detected frontiers. We already have them in image space, and what we can, for example, simply do is make a set of marked prompting to any kind of VLM. We don't need to train this alignment between navigation task and semantic reasoning tasks that VLNs usually need to do. And we can come up with any kind of weighting for any kind of query that we put to the VLM to select the frontier that best matches the query of, for example, go to the living room, leveraging again the whole visual context that is available in the images. And so again, this is how this looks like in practice here. We see on the left kind of the frontiers spawning in 3D space, and the robot starting to explore these. Now here, always skipping kind of different routes because we look for a fire extinguisher and they are not voted high enough by the VLM as something that looks like going to a fire extinguisher. And now we've detected that, so we simply spawn like a last frontier just to move to that object. Now we can take this even one step further. And this is something that we've very recently, this is how the part that I updated now from the ICRA talk, something that we just released a couple of weeks ago, and this is what we call line. So here we in general predict from one image how to move a camera to achieve a certain thing. And that certain thing is, again, kind of just described as a text prompt. So we learn these kind of movements from just egocentric videos that we annotate, just always taking 2 frames, asking what's the difference, how did the camera move? And what we learn now is kind of the opposite. We have a prompt, how do we want the camera to move? And we learn the relative pose. Now this is very interesting because now we can do things like this here, again, without any reconstruction or something like this. We simply say, see what is on the table, and we get a single relative pose of how the camera should move. The camera moves there. And now we can couple this with, of course, other visual models that from just visual space create a certain action or something like this. And in fact, what we see in our experiments is if you couple this together with VLAs that are usually trained on very stationary things and everything should be inside the field of view of the camera, and you now randomize the camera setups a little bit more, we drastically boost performance of these interaction models just by first moving the camera correctly, kind of for them to have everything inside. So kind of here, I find this very interesting because a lot of the navigation research that we've been doing then has also actually a high impact in interactive robotic tasks. Okay, so this, just to wrap up this first part, the kind of things that I want to take out of this, my takeaways from this line of research was that we can solve many navigation tasks without doing any kind of bundle adjustment or dense reconstruction of environments. And that's very relevant because we can now scale these kind of approaches much better to building scale environments, like even kind of whole factory campuses or something like this, because our map representations become much more sparse. And what we also see is that we don't necessarily have to then learn all these navigation tasks end to end, but we have to find really good interfaces, such as relative camera pose or frontiers that we can move to. And these need to be sparse enough such that we can keep them in memory without kind of blowing it up. And of course, all of this is kind of based on that we get really good 3D reconstruction from feed-forward models, and we get really robust odometry these days from all the past research that was put in this lab. Okay, so if we go think and say, okay, we now have these much more sparse representations, we maybe don't take a dense reconstruction, then how does the map representation look like that lets us do other useful things? And my answer here to that is that in my research or in our research, we follow a lot this idea of 3D scene graphs that was put out already by others quite some time ago. A big group that does this is also Luca Calone's group from MIT. So essentially, the idea of a scene graph is to have a hierarchical environment representation. We can cluster an indoor scene into rooms, rooms into floors, floors into buildings, and so on and so forth. And our lowest level is usually objects or object parts, so still very sparse. We can, of course, keep potentially some 3D reconstructions for individual parts, but we don't have to have this whole density across the whole environment, and we might even swap in and out parts from the environment. Now, the nice thing about these representations is, for example, that we can query them quite easily with language models. So we can do something like bring me a certain object, and now all I need to do in the scene graph is I need to select a single node inside of this graph. I query this usually with like flip features or something like this. Now I just take the geometry of this node, I run some graph processing, for example, on it, and I can go and manipulate that node. Okay, let's check for the video. Finish. Yeah, there we go. Okay, the other interesting property of scene graphs is that it's very easy to update these representations from dynamic observations. So what we do here is this kind of teach and repeat setting. We track an interaction through meta-aria glasses, so these smart glasses that give us egocentric data. And if we maybe look once more, then we see if we have a good tracking that we kind of show in this work, then we can very easily update these representations, because all it takes is just updating a couple of pose parameters of one node in this graph. Much easier than it would be for these more dense representations. Now, something that we showed at ICRA is that another nice property of scene graphs is that they are very nice to integrate with LLMs. Without, again, any kind of training or something like this, we can usually process a scene graph into a JSON representation that really simply has the graph information without any geometry. And because these representations are quite sparse, we can usually fit them or make them fit inside the context window of just a single query, which allows us to do very complex queries, of course, that go beyond just retrieval through clip descriptors or something like this. And we can kind of just get responses out of like target nodes or something like this. And because we can couple this still kind of in the back end with kind of more metric representations or some kind of other navigation framework, we can easily navigate there. And that is a task that we can use just classical methods. We don't need any VLM for that or LLM. Now, the interesting property of that is because we can leverage the entire semantic priors and reasoning capabilities of LLMs, that we can locate objects in these maps that have actually been relocated. So let's say we have a first mapping session, then we move around a couple of different objects, something that happens every day in every household that a robot should operate in. Now, of course, a classical mapping framework would allow us to revisit the last location that we've seen that object, but by essentially processing this entire thing through the semantic priors of LLMs, we can, of course, easily guess also other likely locations where that object might be. And that even holds for objects that were not present at all during the mapping session. So something that, again, like these classic retrieval approaches, I just search for the objects that I have in my map, wouldn't work at all for that, because there's nothing to retrieve. Still, the context actually provides us with a good enough guess to find these objects that have not been mapped at all before. Then something that kind of goes now beyond like these classical semantic mappings of objects and so on, as I already said, we can build connections now in these graphs that have nothing to do with any kind of appearance. So a very classical problem for this is you come into a room and you try to figure out which light is operated by which light switch. Now, no VLM in the world can really tell you because these are highly random and not even cultural or something like this. There's no central rule to it. You can very simply find this out, however, by trying out in the environment. So this is, of course, something we can do with robots by interacting with the different light switches, observing the different lamps. And now scene graphs allow us, of course, give us a very good structure to build connections and simply just connect two nodes with these kind of functional connections. So this is, again, a map representation that allows us to include that additional information very easily. Now, to close off, there's a couple of other physical properties that I am very interested in the future to put again into these kind of representations. And this is just something that I don't have the solution yet, but we at least now started to collect data that we can use for these kind of mapping tasks. And it's something I want to advertise a little bit. It's called the Hoi data set. Hoi, like saying hi in Switzerland, but also like hand-object interaction. So we have a lot of these interactions, for example, with these grippers here, but also with human hands. And we measure all kinds of different things, tactile sensing. And one of the things that I'm most interested in is the modality of interaction forces. So we have these couple of different cabinets and ovens and so on. And we know, of course, as humans, that to operate each of these, you need different kind of force profiles. Now, this is something that we, for the first time, measured. I think this is something, again, that is environment-specific information that is super relevant for robots to kind of store, that you remember, okay, you need to apply a little bit more force here. For this kind of cabinet, it's fine. For another cabinet, if you apply that kind of force, probably something is stuck, and you should not do that because you might break something. Now, in this data set, we give you essentially a lot of different interactions. We give you 3 different gripping modalities. We have a couple of robot demonstrations. We give you ego and exocentric views. So I think there's a lot of playground to play around with these kind of future information that we want to put into robotic maps. Now, to conclude all of this, what I started out with is arguing that we can free up some of the space that we so far kept as environment-specific information in maps such as 3D geometry and really dense free space information. And I've shown that there's ways how we can leverage rather generalizing models, priors that robots can bring with them to ad hoc create that kind of information if we really need it, but we don't need to store it all the time. And our maps can kind of rather free up that memory to then store interesting other kind of information, such as object dynamics, interaction experiences, functional connection. And I think something that might be super interesting in the future are also user preferences. With this, I want to thank all my collaborators that actually did the work that I've presented here, both at ETH and the University of Bonn. I'm happy to take some questions. I also put my email here in reach in case you have any follow-ups later on. Thank you.
Awesome. Let's take 2 questions. One is I'll combine 2 of them, and this is in regards to the Open Frontier paper, and there's a question around the performance as well as the benchmarks. And the first one is what metrics were used to measure navigation performance? And then another one is how did Open Frontier perform on HM3D compared to other baselines like UniNet, NAVID, and Unigoal?
Yeah, that's a really good question. And let me just see if I have as a backup actually the results that we had. I don't think so, unfortunately, but I can tell you that, of course, we evaluate in these classic benchmarks. Now, I need to say for this, I'm really not a fan of them anymore. I feel like all these Matterport benchmarks are highly saturated at this point. Still, what we see is with the simple design of Open Frontier, we actually beat most of these baselines. Now, to be fair, and this is something that if you work in this space, you know, there's a lot of tricks in all the repositories to actually get any good numbers. So I think a more fair comparison is also then to really try it out in the real world. We did that as well, and it was working quite well. But kind of, I think my takeaway for this is both in success rate, SPL, and so on, the default metrics that you know, this surprisingly simple approach goes a long way and is definitely competitive with like vision language navigation models specifically trained for these environments that then, if you want to deploy them, actually don't generalize that well anymore.
And then let's take one final question, and this is, I think, from the paper right before Open Frontier, which was just net. And this question is in regards to the ground truth generation uses privileged 3D info to supervise a 2D model. And I guess the question is, how did you arrive to subsampling 10% of frontier voxels as the right approximation?
Honestly, this was a lot of trial and error. And I think this is not necessarily the most optimal choice. It is essentially took us a long while to generate all that data in the first place. Um, and essentially at some point we stopped because we noticed this model already generalizes much better than we expected in the first place. I think if you play around with that, if you have a maybe even more diverse environments or something like this, you might even achieve something that works even better.
Fantastic. And we'll go ahead and leave it there. Thank you very much for the presentation.
Thank you.
All right. And quick reminder, we are recording the talks and we'll be uploading them to the Vox51 YouTube channel. We'll probably clip up some of the highlights as well. So we'll look for those on social media. Thank you very much for the presentation. All right. So with that said, let's do a quick flash demo. Eric, if you're with us, the floor is yours.
Hello, hello. Hey, everybody. Very interesting talks. So yeah, just quick intro about myself. Like Jimmy mentioned, I do work with him at Voxel 51. My name is Eric Hoffesman. I am a project manager and also on our customer success team. I'm a machine learning engineer by trade. And just want to take a couple minutes to talk about some of the cool stuff that we're doing at Voxel. So especially for this audience, there's some pretty exciting new things that we've been working on in the physical AI space. So just a quick recap. If you don't know, Voxel 51, kind of some state-of-the-art tooling around building data flywheels for AI development. So for the last few years, lots of different projects have been building on top of 51 for this flywheel, which it's become really apparent that if you're trying to get some AI model into production, the faster that you can iterate over identifying, where your models are performing poorly, improving your data collection, bringing humans in the loop for annotation and evaluation, and then kind of continuing this cycle as you are refining your model, the faster you can get a high quality model. So in the robotic space especially, there's been pretty exciting developments, especially with kind of all this push towards VLAs and end-to-end models. The tasks are starting to change a bit, as well as the data that needs to be supported for this flywheel. But kind of the core of it is still the same. You still need to be able to curate across your data sets, be able to identify model failures, and then improve your data sets by bringing humans in the loop to be able to start identifying and correcting these different failure modes. So with that, I want to jump into a live demo for a couple minutes of some of the things that we've been working on. So here, this is the 51 app. Again, like Jimmy mentioned, we've got a open source core of this, and then an enterprise offering. So for this type of new visualization that we've got of MCAP data. So this is available in the open source. So here we've got a episode from the Droid dataset. So pick and place robotics dataset where we've got multiple different sensors on this robot, different RGB cameras. We've got some depth information, with 51, you can very easily now be able to bring in this type of multimodal data for visualization, which is the first step of that data flywheel for curation. You need to be able to actually look at what your models, your robots, your data is doing on a scene-by-scene level. So you can kind of bring in your MCAP files. You can customize exactly how this visualization is set up. You can visualize different types of data. You can, customize like the look of the layout here, and then importantly, this is all time synced, so you can play back all of the different topics that you've got in your logs at the same time. And then, the visualization of individual episodes is just kind of the starting point. With 51, to be able to do curation at scale, you need to bring this to a whole data set, and you need to be able to start interacting with these. So let's say that we're looking at this episode and we just want to, see something interesting. This robot's placing this block into a drawer. We can then, for example, add some tags to this. So we can start kind of enriching the data set with more information. So robot places object in drawer, can add a tag to this episode, and then we can pull out to our entire data set of all of the different episodes that we've got from, in this case, this robot across many different tasks. And then with a click of a button, we can then find some of the tags that we've specified. So this is a great way to be able to start kind of starting with curation. I'm going to jump over to another data set. So if you're not working with, like pick and place robots, there's really any type of data, no matter what use case that you're working on. If you're working on physical AI projects, you're going to be able to use 51 for your data flywheel. So for example, if you're working on autonomous vehicles, you can bring in those MCAP files, be able to visualize all of your vehicle sensors, GPS coordinates, IMU data, LiDAR sensors, as well as all of the different like annotations on top of that. For example, if you've got object boxes, and then again, you can not just visualize individual scenarios, you can actually curate at scale. So I've shown you how you can add custom events. You can also query you can index and query across any of the metadata that you've got on your data sets. So for example, with just like a click of a button, we can find samples where the vehicle had like a high peak speed, and then immediately filter down for these episodes where the vehicle, for some reason had a really high speed, and you can see that there's some school zones in here, so might be a little concerning. So that's especially something where you'd want to kind of dig in and see what's happening. So as you do that, you can start to understand what's in your data set, but it's also not just manual and like indexed metadata that you can review. With 51, we also have some other intelligent ways for you to curate your data. So for example, you can take models that can embed the different sensors that are in your data sets, and then you can visualize those and actually explore the data set in this embedding space. So here, each one of these points corresponds with one of the episodes in this data set, and we can see some different clusters. We can also color these points by different metadata that we have. So for example, here in this cluster, we've got these scenes that are being pulled up, and it looks like there's some different kind of like environments here, but similar tasks. And then here, if we color it, we now see that each one of these points corresponding to an episode is colored by whether it was a successful or a failed attempt at the task. And a lot of these clusters kind of seem, like mostly success or mostly failures, but there's this interesting one where for some reason all of these episodes have like a mix between where the robot succeeded or failed. So this is also where you can then bring in kind of the humans into the loop in your data flywheel. If you find something like this, where you've got kind of a subset of data that you then want to get in the hands of some people for review or re-annotation or evaluation, we can lasso this and we can save these as a view of this data set. And then from there, we can then jump over into this annotate tab and create a project for review of this subset. I can create some annotation tasks. So I'll say for this review of failures, we'll then send these to some annotators, kick off a workflow, and then be able to start kind of coordinating with potentially multiple people if there is a lot of data that you've got to go through. Of course, if it's just a small amount of data, you could do this yourself, but this is a way to start bringing in more folks. So within this annotation experience, you can review individual episodes, you can tag them like I was showing, and then you can also annotate all kinds of other things. So for example, if you've got like chain of thought captions from a VLM, you could review those. And then you can easily submit different samples in this annotation workflow. And if you see some issues, you can edit the labels, the events, as well as any of these captions. And it's very customizable, so you can also tweak a lot of these UIs to fit your specific use cases. Like in this one, the robot is picking up some clothing, and then it tries to grab this shirt, and it accidentally grabs the chair instead. So the outcome here was not necessarily that it slipped, but instead that robots accidentally grabbed chair, for example. And we can save that and then go on to the next one. So with that, you can see how it becomes especially useful to just in the same platform be able to go from visualizing your data, curating it, bringing in models to be able to really evaluate and explore your data set to find failure modes, and then being able to scale that up to large data sets and large human-in-the-loop workflows. So that is kind of how 51 helps you build out these data flywheels for really whatever physical AI task and project that you might be working on. And with that, I will pause there and then toss it back to Jimmy. Thanks for the time.
Fantastic. Thank you, Eric. So I've included a link there if you want to pursue 51's multimodal capabilities more. And then don't forget, we got a couple of workshops on this topic coming up as well. So make sure to check out the Vox 51 events calendar to get hands-on with the stuff. Thank you, Eric. So with that said, I think we are ready to move on to our next speaker, which I think if I look at my notes means that Zhenjun, if you're with us, the floor is yours.
Okay, thank you. So let me share the screen now.
We see.
Okay. Okay. Thanks for the organizer. So hello everyone, I'm Zhenjun Zhao, a postdoc at the University of Zaragoza, working with hardware Sierra. So today I will talk about my recent works, which is trustworthy geometry, perception, certifiable optimization, and robust estimation. And this talk will be divided into 3 parts. So first, motivations, and second, 3 recent works of mine, and finally, some open challenges in global optimization. So first, motivation. So why we need trustworthy geometry perception? Traditionally, geometry problems are often formulated as non-linear optimization problems and solved using local methods such as Gaussian-Newton and some existing local solvers. However, the highly non-linear and non-convex nature of both objectives and constraints makes local methods sensitive to initialization and fails silently. Furthermore, no optimality guarantee. So we need certifiable optimization. We need globally optimal and certifiable solutions. We should know when it is correct. And 2 research directions in my research in the trustworthy geometry perception. certifiable global optimization, convex relaxation, and polynomial methods providing formal optimality guarantees, and which is also our recent ICRA workshop paper, and robust estimation perception reliably under motion blur, dynamic scenes, and featureless environments. For robust estimation, you can scan the QR code for more details, and I will focus the first direction in this talk. So that's the first part. Then let's move to the second part of this talk. I will introduce 3 works in the certifiable global optimization. First, Globust VP, convex relaxation for robust vanishing point estimation in Manhattan world. In a 2D image, lights that are parallel in 3D space appear to converge at a single point known as the vanishing point. A space containing 3 orthogonal sets of the parallel lines is referred to as a Manhattan world. Vanishing point is a fundamental concept in 3D vision, with broad applications such as structure from motion, simultaneous localization and mapping, camera rotation estimation, and structural understanding. In this work, we address the problem of joint vanishing point estimation and line label from a single image given a set of unlabeled line segments and the camera's intrinsic parameters. Our goal is twofold. First, to correctly assign each line segment to its corresponding vanishing point or to an outlier class. Second, to estimate the locations of each vanishing point. In this paper, we evaluate each method according to the following criteria. Global optimality. The solution must be global optimal. Efficiency. It must be practical. Outlier robustness. It should handle outliers reliably. Generalization. It must work across diverse data sets. There are 3 lines to address this problem: ransack-based, branch and bound, learning-based. However, they cannot simultaneously achieve all criteria described above. Our method, Globust VP, is designed to overcome the trade-offs listed in previous approaches. It's built on 3 insights: problem reformulation, convex relaxation, and iterative acceleration. Through these 3 insights, our method satisfies all 4 criteria introduced before. Let's begin with the first insight. Given the problem of joint vanishing points estimation and line labeling, we find the core difficulty lies in how to represent the discrete labels. Our core idea is to introduce 2 continuous constraints. The first, a quadratic constraint, enforce every label to the either 0 or 1. The second, a linear constraint, ensures each line to be associated with only one vanishing point or the outlier class. Given all lines, we can collect all the labels into a permutation matrix. Consequently, we can get the corresponding matrix-wise constraints. The overall problem formulation includes 3 key components. First, the objective function, as we just discussed. Second, the matrix-wise constraints on permutation matrix. Third, the Manhattan constraints on the vanishing points, which enforce their mutual orthogonality. With such insight, we can successfully reformulate the hard assignment problem into a continuous constraint optimization problem. As a preliminary step for insight 2, we lift the variables of the primal problem into a higher dimensional space. This leads to an equivalent formulation, constraint quadratic program. However, this QCQP is non-convex. As shown here, non-convex problems often contain multiple local minimals. To overcome such non-convexity, we apply a powerful technique, which can relax the QCQP to a convex problem. First, we construct the Lagrange dual of the QCQP, which gives us a convex dual problem. Then we take the dual of that dual problem, arriving at the final dual formulation. This transformation is known as convex relaxation, and the resulting dual formulation is actually a convex semi-definite program, or SDP. This SDP can be solved globally using any off-the-shelf solvers. A critical property is that if the relaxation is tight, the solution of the SDP is exactly equivalent to that of the original NP-hard QCQP. Through convex relaxation, our method not only guarantees global optimality, but can also handle a large proportion of the outlier. Although the SDP formulation guarantees global optimality, solving it with all lines and all vanishing points simultaneously can be computationally expensive, especially in large scenes. Our third insight addresses this challenge through our iterative acceleration strategy. Instead of solving one large SDP, we estimate vanishing points one by one. In the first iteration, we estimate vanishing point 1, treating all other lines are outliers. In the second iteration, we remove lines assigned to vanishing point 1 and estimate vanishing point 2. Finally, in the third iteration, we follow the same procedure to obtain vanishing point 3. Our method, Globust VP, is designed to overcome the trade-offs in the previous approach. It is built on 3 insights. That's the 3 insights. We also compare our methods with we compare our methods with the BNB and RANSAC under different levels of outliers in terms of accuracy. Our method consistently outperforms both of them. It even maintains high F1 score under 70% outliers. In the terms of efficiency, as shown in the runtime comparison under 20% outliers, our method is comparable to RANSAC and significantly faster than BNB. We evaluate global Bust VP in the real-world datasets. As shown here in both subway and building scenes, our method achieves a perfect F1 score and minimal consistency errors, significantly outperforming RANSAC and BNB. We also compare with learning-based approaches such as Neural VPs and PASEC on the YOD and SU3 datasets. Our method outperforms both approaches on YOD and achieves comparable performance on SU3. This difference highlights a common limitation of learning-based methods. While they perform well on datasets similar to their training data, such as SU3, they often struggle to generalize to more diverse or unseen datasets like YOD. Second work, NPC neural predictor character solving homotopy problems with reinforcement learning. The homotopy paradigm is a highly versatile problem-solving framework, widely applied in tasks such as robust optimization, global optimization, polynomial root finding, and sample. Although the specific details vary, their core algorithm architectures are remarkably similar. Specifically, a homotopy problem consists of outer and inner layers. The outer layer is the constructed homotopy interpolation from a simple source problem to a complex target problem. The inner layer is the implicit solution trajectory that we actually need to check. The focus of our work is not on realizing the homotopy process itself, but rather on how to advance along this implicit trajectory more efficiently and speedily. Traditionally, the predictor-corrector method is the standard algorithm for tracking such trajectories. Its workflow is intuitive. The predictor first takes a step forward to estimate an initial value, and the corrector then iteratively refines this prediction back onto the true solution trajectory. However, many key strategies in this process, such as what step size and the predictor should take and when the corrector should stop, rely heavily on human experience. These heuristic rules are often inflexible and far from optimal. To address this issue, we propose the neural predictor corrector, or NPC. As you can see on the left, the classical predictor corrector relies on fixed manual heuristics for its step size and correction tolerance. In constraint, our method on the right replace these manual heuristics with our neural networks. Compared to the classical approach, the neural predictor corrector can automatically discover the optimal control policy at each step. To achieve this, we formulate the entire corrector process as a sequential decision-making problem and utilize reinforcement learning to learn the control policy. And at each homotopy stage, the model observes the current state from the environment, including the homotopy progress, statistics from the previous correction step, and the convergence velocity. Based on this state, it outputs the next action, the step size for the predictor, and the correction tolerance for the corrector. Finally, our desired reward balances accuracy and computational efficiency, guiding the model to find the optimal trade-off. To validate the university of the NPC, we conducted experiments on 4 typical classes of homotopy problems: robust optimization, global optimization, polynomial root finding, and sampling. It is worth emphasize that we adopted an amortized training mechanism with just a single offline training session on the training set, and the model can directly achieve zero-shot generalization on unseen test sequences. These 4 tasks are: first, robust optimization based on GNC, which smoothly transitions from a smoothed objective back to the original non-convex objective, that is, 2 outliers. Second, global optimization based on Gaussian homotopy, which simplifies the objective landscape through Gaussian smoothing and then tracks back to the global optimal. Third, polynomial root finding based on homotopy continuation, which continually tracks the root trajectory from an unknown simple equation to the target equation. Fourth, sampling based on annual lagging dynamics. NPC can learn how to efficiently advance 3 intermediate distributions, providing that our method can also seemingly extend to sampling scenarios. Next, let's look at the experimental results. In the point cloud resolution and multi-view triangulation tasks, NPC reduce the total number of iterations and run time while maintaining or even lowering the final error. This proves that NPC has indeed learned on more reasonable scheduling strategy, avoiding meaningless computational overhead. The same advantages have been verified in the other tasks. In the other tasks, the number of iterations in global optimization is significantly reduced. In the polynomial root finding tasks, NPC maintains a 100% success rate with total time consumption lower than classical methods. In the sampling task, NPC reduces the computational cost while ensuring that sample quality metrics such as KSD remain close to those of classical methods. The final work, a survey, advanced in global solvers for 3D vision. We formulate, we survey. This is the overview of this survey, and we divided three parts of the survey. The first is the global solvers, and the second is analysts, and the third is the applications. We categorized global solvers into three main families based on their underlying principles: branch and bound, convex relaxation, and graduated non-convexity. We provide a comparison of the global solvers, examining trade-offs in optimal guarantees, computational complexity, and scalability, outlier robustness, and practical deployment considerations across different methods, families, and method families and problem scales. We survey how global solvers have been applied across classical 3D vision problems, including Wahaba problem, vanishing point estimation, absolute and relative post estimation, 3D registration, rotation and translation averaging, triangulation, post graph optimization, and bound adjustment, highlighting algorithms typical performance trade-offs and open gaps. That's the second part. So final section, open challenges. Three open challenges are highlighted. First, scalability. The global optimality guarantees provided by branch and bound and convex relaxation methods come at significantly computational cost, with complexity growing for large-scale problems. Addressing this scalability bottleneck while previously certifiable remains a central challenge. Second, how to combine deep learning with global optimization. Foundation models produce impressive predictions without certificates, but impressive not equal to certifiable global optimal. So this is indeed a direction to study and research. Third, evaluation. The field lacks benchmarks and evaluation protocols for comparing global solvers across different problem domains and scales, hindering progress and fair comparison of the method. So thanks for my amazing collaborators. Thanks. Any questions?
Yeah, let's take two questions. And first question is around the Globust VP paper. And I think, let me summarize the question here. The Manhattan world assumes three orthogonal directions. Do you see a path where you can extend this convex relaxation approach to Atlanta world? And I'm assuming Atlanta world, we mean interior environments where there are more general non-orthogonal scenes.
Sorry. So for the specific for the.
So the question is whether the Manhattan world assumes three orthogonal directions, and then the question, do you see a path where this work can be applied to Atlanta world problems or more general non-orthogonal scenes?
You mean the Atlanta and like the Hong Kong word, like Atlanta word? You mean to generalize, generalize to more general problems or word?
Yes. So I'm assuming by Atlanta, we're mean a geometric model of indoor and urban environments.
Yeah. It's for sure to generalize the more general words, because you can see the inside three iterative acceleration. We iteratively solve the vanishing point estimation. So no matter what's the number of the vanishing points in the world, in the environment, we can iteratively estimate every vanishing point. So just for this work, it's just for the Manhattan world, but you can apply these solvers and apply this convex techniques to the more general world, like the Atlanta, like the Hong Kong world. Okay, yeah.
Fantastic. And then we'll take one last question. This question came during the global solvers part of the presentation. And the question is, it looks like you guys deliberately excluded sampling-based methods like ransack from your scope. Can you say a bit more about why you drew this boundary?
Mm, we don't think the ransack is a global solver because the sampling based method is has a inherent limitations, like the because it is based sampling, so we cannot get the determinist solution for the every trials for the problems. Like like you use the ransack or other sampling based methods to address the same problems, but every time you can get maybe you can get not the same solutions. So I think first the sampling based methods are not included in the global optimization. And in terms of the boundary, I think ransack or other sampling methods, the advantage of they're very efficient. So we can use the efficiency, this advantage of the efficiency to consider into the truly global optimizations. So yeah.
Fantastic. And we shall leave it there. Thank you very much for the presentation. Quick reminder, all the talks are being recorded and we'll upload those to YouTube on Wednesday. Thank you very much.
Thank you.
Okay, if you want to stop your share, perfect. That means we're ready to go to our third speaker. Jing, if you are with us, the floor is yours.
Thank you so much. Let me share the screen.
Perfect.
All right. Hi, everyone. My name is Jing. I'm currently a postdoc at Stanford Robotics Center and the Stanford Center on Longevity. So today I'm going to talk about our recent work, the outdoor robot navigation in unstructured world. So in the following slides, I'm going to introduce our work in long-range navigation, and it covers both on-road and off-road navigation. So what is robot navigation? Robot navigation is a process where, given a goal, a robot will plan a path and autonomously move to the goal while also responding to the surrounding environment. So robot navigation can have a really significant impact on everyday life. But the outdoor applications, last mile delivery robots can make goods and services more accessible and convenient. And about the indoor applications, warehouse robots can improve both efficiency and safety by taking over the transportation and lifting tasks. So more broadly, autonomous robots can handle tedious or physically demanding work and allowing people to focus more on decision-making and higher value tasks. So the problem we are working on is the long-range navigation. It requires robots to perform autonomous navigation over a really long distance in complex terrains. So long-range navigation is really hard because it's not a single problem. It's a systematic problem, which has lots of challenges. It requires the localization, routing, perception, trajectory planning, and real-time motion control to work together reliably. So a common approach to long-range navigation is to build a really accurate map, global map, and plan a path within that map for robots to follow. However, constructing and maintaining a detailed map can require substantial time, computation, and also human effort. So to reduce this dependency, we assume that owning a satellite map and GPS are available for global routing and localization in our scenario. But one of the challenges is that the GPS signals can be really inaccurate, especially when the robots are moving around the tall buildings or in the areas with really poor satellite visibilities. And the second assumption is that the scene understanding relies entirely on the robot's onboard sensors. So we do not assume any external sensing infrastructures or human guidance. And so compared with autonomous vehicles, for small robots, they operate under quite different constraints. So they usually have more limited sensing, computation, and battery capacities. And they also move through sidewalks and unstructured outdoor environments where they must reason carefully about terrain traversability, vegetation, pedestrians, and some social context. So one major challenge is the traversability analysis. The robot must determine whether the terrain is traversable given its own mobility and dynamic constraints. For example, as shown on the left bottom figure, the legged robots can cross curbs and stairs, while the wheeled robots can generally move around the smoother or more continuous surfaces, as shown in the left top figure. And also another challenge is that during navigation, the robot must also understand the traffic and the social rules, as shown in the figure on the right side. So to address all those challenges, we developed an approach called MOSU. It is a three-stage system for long-range outdoor navigation. So the first stage performs global routing and generates sub-goals that guide the robot in correct direction. The second stage analyzes the local perception, generates candidate trajectories, and select both a trajectory and a velocity mode for robots to navigate. And the final stage handles real-time motion and follows the selected trajectory from the last stage while also doing collision avoidance. And for the global routing, we use a satellite map and continuously update the navigation sub-goals. And these sub-goals provide the robot with only a rough direction rather than a very exact local target. So because the robot doesn't need to reach each sub-goal precisely, so compared with the approaches that rely on accurate map-based waypoint tracking, the system is more tolerant to the GPS noise. So this video shows how the routing models update the sub-goals during navigation. The red marker indicates the upcoming sub-goal, and that guides the robot along the global road. The second stage analyzes the robot's local observation and produces a trajectory of up to around 20 meters together with a velocity mode. And this stage must evaluate terrain traversability, understand social and traffic conditions, and choose a trajectory that moves the robot towards a current sub-goal. And we use three main components for this task: a trajectory generator, a traversability segmentation model, and a vision language model to evaluate the social and traffic cues. And for traversability analysis, classical approaches usually combine the geometric local map with RGB semantic information to estimate the traversabilities, and then plan a path to a goal. These representations are very useful, but maintaining a really large geometric map can be computationally and memory intensive. Since ultimately we need to generate trajectories for navigation, and the trajectories are in very low dimension. So instead of building a really large geometric map and do a path planning for like 20 meters, we can incorporate the geometric information by directly generating feasible trajectories. So finally, we convert this problem from really high-dimensional local map building to a trajectory generation problem. And we generate diverse trajectories to cover all traversable areas in front of the robot. So in this approach, we use conditional variational autoencoder-based generator to generate diverse trajectories. And in the middle of this process, we linearly projecting the embedding vector into multiple diverse embeddings. And each of these projected embedding vector corresponds to a trajectory. So in this work, we also use a really big data set called GND dataset to train the model for different types of robots, such as leg robots and wheel robots. And also in the CVE formulation, the latent embeddings modeled as Gaussian distributions. So we can use the variances of these distributions to estimate the confidence of the generated trajectories. In the training, to improve the generalization across different environments and robot platforms, we created the GND dataset. The dataset contains 5 traversability categories and covers 10 university campuses around the Washington, D.C. area. And it includes around 11 hours of recorded sensor data across the environment containing more than 350 buildings. And we also open source the data collection and also processing pipeline to support future contributions. And this slide shows one example collected at George Mason University. The dataset includes 3D LiDAR, a front-facing RGB camera, 360 camera, MU GPS, and also view odometer. So this is a video demonstration of the trajectory generation method. So in the video, the darker color means lower confidence, and the lighter color means higher confidence. And the top left figure shows the selected trajectory, which is both high confident and also closest to the target. And the top right figure shows the third-person view of the navigation. And we also use a dynamic window approach as a motion planner to follow the generated trajectory for collision avoidance. And we can see that the generated trajectories can cover most of the traversable areas. But from this video, sometimes we can also see that in some of the scenarios, those are out of distribution cases, and the trajectories are not very traversable. So this is the next challenge we need to solve. All right. So as shown in the last video, the purely learning-based trajectory generator has limitations, and the real-world environments can contain lots of out of distribution conditions, because our data set is not really big enough to handle to make the model fully generalized to all those environments. So to reduce this risk, we use the semantic segmentation to filter out the trajectories on non-traversable areas. So semantic segmentation is very useful for identifying terrain classes, but it's not so sufficient for higher level context understanding. For example, it may not be reliable to determine how the robot should behave at the crosswalks, or how it should respond to the pedestrians or the groups. And so we also need to handle this challenge to understand the social and the traffic cues. So we therefore introduce the vision language models to reason about the social and traffic context. So in VLTJAX, we use Gemini to rank the trajectory candidates. and assign one of the three velocity modes. The velocity modes include normal speed, slow, or stop. And the model considers four main criteria. The first, the selected trajectory should remain within the traversable areas. And the second, it should follow social conventions, such as yielding to pedestrians and avoiding passing through the groups. And third, it should respond appropriately to traffic cues, including the crosswalks and the traffic signs. And finally, the selected trajectory should lead the robot towards the current sub-goal. This slide shows the qualitative result of VLTJS, and the top row compares candidate trajectories from several navigation methods. And the second row shows the trajectory selected by VLTJS in red. And while the other candidates also show in gray. So across those examples, the method handles vegetation, curbs and crosswalks and corners while selecting trajectories that are both traversable and following crosswalk when the robot go crossing the street. This video briefly shows how the pipeline works in navigation. The red trajectory is the generated candidate trajectories, and the green trajectory is selected by the vision language model. So after integrating all the components together, we did experiments for outdoor navigation, and the entire travel distance is around 500 meters, and it includes various scenarios such as the sidewalks, different buildings, obstacles, and also vegetations. And we also have pedestrians on the road, and we also have the scenarios with crosswalks. So when we go to the later part, so for example, when the robot meets pedestrians, we can see that VLMs also provide the robot's velocity mode, and it ranks the trajectories and provide reasons behind the ranking. So we can see the robot can follow the sidewalks and follow the roads planned by the GPS, and the robot can also see the crosswalk and follow the crosswalk when crossing the street. And we also conducted additional experiments in various locations, including city and county areas with different terrains. And the method was also implemented on multiple robot platforms, including both the wheeled robots and legged robots. And also in the bottom right video, at the end of this video, we can also see that the legged robots are able to go over the stairs, which means that we can also, for different types of robots, we have different traversabilities. All right, so by moving the robots from on-road terrain to off-road scenarios, there are more challenges. First, the off-road scenarios may contain dense and unstructured vegetations that robot has to find the gap to move through. And the second, the terrain may also have varying physical properties, such as friction, stiffness, and roughness. And these properties also have a big impact on off-road navigation. And third, the labeled data for these physical properties in outdoor environment is very limited, which makes the purely supervised learning very difficult. So in our work, we cannot apply learning-based approaches to train the trajectory generation models because of the data insufficiency. So we come back to the classical approaches to maintain a local map, and we leverage the Gaussian splatting methods to render the environment around the robot with semantics. And to make the local map more accurately represent the geometric shapes of the environment, we also fuse the LiDAR information by Euclidean signed distance field. And then we integrate all the maps together and get the local map for planning. But semantic labels alone are not enough to determine whether the terrain is traversable. For example, when going through very dense vegetations, the robots needs to know if the vegetation is pliable to drive through. So on top of the Gaussian splats, we jointly estimate the semantic material types and physical properties. Considering we don't have a very good data set for learning outdoor terrain physical properties, we utilize VLMs to provide the guesses of multiple observations. And we fuse those values together by Bayesian inferences. As shown in the diagram, we estimate the material labels and physical property cues, and we also estimate the confidences for the regions in each image. And then we use those values to estimate the real material identity and also continuous physical properties using Bayesian inference. The continuous properties include friction, hardness, stiffness, and density, and they are estimated by Gaussian posterior, as shown in the equation, the first part on the right side. And the semantic material types include grass, wood, and soil, and etc. And they are estimated by the Dirichlet categorical posterior at the second part on the right side. This table tells how VLMs work in estimating the friction, stiffness, and the uncertainties. So we can see it's relatively good in estimating the parameters, as shown in the third column. The areas with water have very least friction, as the blue part, and then the grass has higher friction, the purple part, and then the soil and the pebble terrain has the highest friction, the orange part here. So it has relatively good estimation in estimating the physical properties. So from the robot observation, in this video, we can generate a local map for planning. And in the local map, the red color indicates the non-traversable areas, and the green and gray points Gaussian splats. So from the video, we can see that using the Gaussian splats map, we can plan a path to move the robot through the unstructured terrain. So to summarize, we developed a long-range outdoor on-road navigation framework that connects global routing, direct trajectory generation, contextual trajectory selection, including understanding the social and traffic cues. And we also developed a Gaussian splatting-based local map with physical scene understanding for off-road navigation. So the goal is to enable small robots to navigate not only around obstacles, but also through environments that require reasoning about terrain, traffic, people, and physical properties. Thank you so much. I'm happy to take any questions.
Let's take two questions. The first question is in regards to the GND data set, and I think I'll combine two questions into one. So the comment is, or the question is around the 5 traversability categories. I think you had walkways, roadways, stairs, off-road terrain, and obstacles. Were there other categories that you considered and dropped? And if so, why? And then I think a follow-up question there is the sensors that were on the robot. Why did you decide which sensor to use?
Yeah, it's a really good question. So the dataset was designed for long-range navigation only for lagged and wheeled robots. So basically, we choose these categories based on the those mobility of these robots. For example, the major difference between the lagged and wheeled robot is stairs and curbs. Right, so we have those the traversability. So for stairs, actually one of the traversability contains both stairs and the curbs. And another traversability, for example, the road, which is all traversable for all sort of robots, right? And also we have the off-road, off-road, sometimes it's traceable for the wheel robot, but and also the leg robot. But for the vegetations, they are not, right? So mostly the traceability are selected by just the mobility of those two types of robots. And also in terms of those sensor data, because we think for long-range navigation, the GPS is pretty necessary for localization because it's one of our assumption. And to really understand the environment, including both physical and geometric information, we think maybe LiDAR, so we should have some sensors to incorporate the geometric information. So LiDAR is one. And so previously we only mounted the front camera, RGB camera, but we figure out maybe it's not really sufficient to capture the like everywhere out of the vicinity of the robot. So we also have this 360 camera. This is a major reason. So we want to capture all the information, necessary information for robot's navigation.
Excellent. And then we'll take one last question, and this is in regards to MOSU, and I'll try to paraphrase here. You spaced the GPS subgoals about 50 meters apart with a 10-meter proximity threshold. How did you land on these numbers? I'm assuming it wasn't arbitrary.
Yeah, it's a really good question. Yeah, so previously we also tried this GPS. Our GPS model is not really accurate. So around the buildings, especially tall buildings, the accuracy is around 10 to 20 meters. So the variance could be 10 to 20 meters. So that's why we choose waypoints to cover this the noise. And also, so yeah, this is a major reason. So it depends on our GPS model.
Fantastic. And I have included the links to the MOSU paper as well as the GND paper if you want to pursue it. Thank you very much for the presentation.
Thank you.
Awesome. Okay, well, that means that we are ready for our final speaker, which means that Ashis, if you are with us, the floor is yours.
Thank you so much.
Looks good on this end.
Okay, thank you. So today, first of all, thank you for organizing this meetup. Lots of interesting presentations already, and hopefully mine would also be of some relevance to the audience. It's gonna cover a slightly different topic. So I'm mostly gonna focus on the recent paper that we presented at ICRA on object 6D pose estimation and tracking, especially in indoor cluttered scenes. But before going there, I want to talk about some of the broader scope of work that we are doing in my research group at the University of Washington in Seattle. So we are, or one of our big research thrust areas is on robust and generalizable robot perception for autonomous mobile robots, specifically mostly looking at indoor robots. And we are mostly motivated by the problems of how to make these robots be deployable in indoor settings. Could be like homes, public spaces for long-term autonomous operations. And there we, of course, know that the scenes are gonna change, new objects are gonna show up, and the robot has to figure out what those objects are, how they can be manipulated for, and other downstream applications like those. So we believe for at least these kinds of long-term autonomy and deployment type problems, we really need methods which can leverage like the structure of the environment, which could come from like the shape of the objects or the dynamics of the environment, and like it's gonna be very challenging for pure end-to-end like visual learning methods to work exhaustively in these kinds of scenarios with the types of shifts that we expect in the test time particularly. So with respect to that, we started first working on a kind of robust object detection and recognition. And that's not the focus of my talk here, but I'm just going to quickly summarize the work that we have done over the past couple of years. And we published a couple of papers. You can see the links here, including the code and the data set also that we generated. So our idea here is that we want to have like very kind of frugal or minimal sort of training that can be done entirely on synthetic images. So it's not going to rely on any real world data for training, or at least not as much as possible. So we assume so far that we do have like CAD models or mesh files for the objects. Right now, we are working on some new techniques that can potentially remove that restriction. But so far, what the results that we have, I do assume that we have these CAD models or mesh files. And then we like synthesize lots of images or views of these objects, and then essentially rely on some very interesting topological descriptors to like come up with like 3D shape and also color based or appearance based features that can capture the realization of these objects at a higher level of granularity than what we can typically specify otherwise in the end-to-end sort of learning models. So there is a lot of technical details on how we do that, and I don't think I have the time today to get into that, but I do encourage you to check out the details of how we manage to execute it, again emphasizing that we do not use any real world data for training these descriptors, and then once the features are generated, you can feed them to very like simple classical classifiers, like a very simple neural network or even like an SVM, and you can still do the recognition in a robust manner. So here is like a quick demonstration on the low-cost robot hardware, and you can see it's in an like a fairly cluttered indoor scene with low lighting conditions. We try to kind of mimic some kind of warehouse type scenes, and we compare our approach, this topology-inspired approach, with like a vision transformer model. And in fact, we give some extra benefit to the vision transformer model. It does have access to some real world data. It has been fine-tuned on both synthetic and real world data. And we are dealing only with synthetic data for our model, and it still performs a lot more accurately and generalizes much better to unseen scenes. And and we see like the benefits actually increasing when we get to more and more of these highly occluded or cluttered scenarios. So that was pretty interesting to us. So that kind of led us to start thinking about, okay, this is just like a recognition which can help with semantic mapping and other things. But ultimately, when we want the robots to start manipulating objects, we need to also be able to like perceive the 60 pose and track those poses of the objects robustly in real time. Of course, there has been a lot of ongoing work in this field broadly in computer vision. And we started using some of those like even pretty recent ones like foundation pose and all. And we realized that while they are like fairly accurate. They are not very suitable or yet, at least for real-time applications where we want to do complete onboard processing on robots, and which means we have to make them work on edge devices, which can be GPU processors, but it has to be edge devices, so it's not any centralized computation. And we want it to run alongside full autonomy stack of the robot, which means it has to do everything else, including navigation, mapping, and then manipulation planning, motion planning, all of it. So perception cannot like consume the entire processing resources. So we wanted something which is at least comparable in terms of accuracy, would generalize well to unseen objects, and most importantly for us for this work at least, was to make sure it's lightweight enough that it can run in real time at least like 5 frames per second or more speed on a robot. So those were like our specific goals as we started thinking about how can we again exploit some structure in the objects that the robots is viewing to be able to do their pose estimation and tracking. So the key idea there we came up with is this notion of color pairs. So we're not talking about, again, individual colors, but color pair, and it's kind of visualized it here. Individually, we know like the colors change quite a lot depending on your ambient lighting conditions. But if we, assuming we have fairly rich texture or color information on the objects, we have many kinds of colors, and we can look at those in a pairwise manner, or maybe in the future as more of n tuples, and try to identify some associations or correspondences among these pairs of colors, which would be a lot more robust to like the background lighting conditions. So one of the things that we did was to convert everything to the Scilab color space rather than maybe the RGB or the HSB. So that makes it more the representation of the color in terms of chrome and luminosity a lot more robust. So we did that, and then we created these kinds of triangles with these colors nodes as the vertices of the triangles, and came up with a bunch of different sort of handcrafted features to characterize the geometry of these color pair triangles that we constructed. And we can find more details in our paper. So things that we considered would be like the relative contrast, their relative luminosity, as well as their directional alignments. And then the idea was that using these color pairs, we can have sort of a unified framework which can do both pose estimation. That means this kind of a zero shot thing, like the robot first views the scene and it estimates the poses of all the objects. And then as it moves around in the scene, it can still kind of robustly keep tracking the pose. So we use the same sort of unified features of color pairs to do both pose estimation and tracking, and again in real time. We do use neural networks internally for some of the processes, but as you can see here, it's not reliant on very heavyweight architectures with pre-trained encoders. So this is kind of the overall pipeline. again, one of the similarities here with what I was explaining earlier for object recognition is that all the sort of offline like training slash kind of model preparation processing is done purely based on like synthetic images. This is again not using any kind of real world data in that phase, the offline phase at all. But it again has the same sort of restriction as earlier, that we assume that we know the overall object categories and we have access to like the mesh files or CAD models of these objects. So we again render these objects from a bunch of different views. You will see that more in a subsequent slide. And for all of these different views, for all of these objects, we do this color pair extraction using those triangle-based features that I talked about. And then online, you can see that there are two kind of branches. So one side, we have the branch for the zero-shot pose estimation, and then we have on the right-hand side of the figure a branch for the optical flow-based pose tracking. So the common part for both these branches that are happening online is that from the depth camera images, we like get the actual like image, segmented image. So we do have to do like object segmentation. So we get segmented the map of or mask of the object from the depth camera in real time. And then from there, we have a very similar color pair extraction scheme as we do for the offline rendered views. And then we do this kind of classical matching and comparison, but now at the color pair level, using again some specialized technique that I'm going to talk about a little bit more in detail, which generates some corresponding like point clouds. You have some reference point clouds from your offline library. You have the query point cloud, and then the rest of it is almost the universal ICP method, which is slightly customized. We do some initial pose voting based on, again, the color matches. So that's what is happening on the pose estimation side of things. On pose tracking side of things, we use, again, the classical optical flow method, but try to make it more robust, because anyone who has worked with optical flow knows that if there are some kind of jerky motions or some like maybe missing frames, then like the method tends to lose its accuracy quite easily. So we kind of boost the optical flow-based tracking method with our color pair-based filtering to make it more robust. And we, in fact, do some tests where we artificially like do not feed certain frames, consecutive set of frames to the method. We skip a bunch of frames and then we give like a frame after a while, and then our method is still able to sort of, in a continuous sense, be able to track the object's poses in real time. So that's the overall goal. So a little bit more details about the individual steps of the pipeline. So they are fairly simple and intuitive, nothing too fancy going on here. So for view generation, it's again a simple idea. It's all synthetic rendered image. So we choose like 14 views to get a decent coverage from different viewpoints. For the color extraction, before we can construct the color pairs and all those triangles and all, we have to extract the colors themselves. So that's based on a combination of like the gradient along the two axes and their magnitudes. The surface point classification is again pretty straightforward. And then one of the other things before we run the ICP method I was talking about is this initial pose voting. So there we again leverage all these color pairs that we have already extracted and the triangles that I spoke about, and look at those triangles from a slightly different perspective with some more semantic labels associated to it, and do some comparison of these semantic color triangles before we feed them to the ICP method. So that helps with getting good initial poses as the seed points to the ICP method. Again, for anyone who has worked with ICP would know, like, the quality of the results or how quickly converges depends a lot on your quality of the initial pose guesses, and looking at these relative or weights of the probable poses as the initial seed points using color pair information helps a lot with the performance. Okay, so this is more of that. And then this is kind of an illustration of how we use these color pair based point clouds also to boost our optical flow method. To essentially, you can think about it as kind of an outlier filtering or noise removal type scheme that's added on top of optical flow. So with that, finally, the last step in order to do the post tracking is our version of the PNP algorithm. So there we do use DGCNN, graph convolutional neural network, attention with an attention head. So that is, I would say, within our overall pipeline, the most kind of computationally expensive step, but since this is the only time we are using it, and we are using like a fairly small set of kind of handcrafted features, it works efficiently, and in fact it works quite fast in real time, as you would see in some of the results. Okay, so we did some benchmarking both on the estimation side, pose estimation side, and on the pose tracking side. So for pose estimation, we used the very popular YCV video data set. It has a fairly decent number of object classes, some with symmetries, and also it's widely used for it's a good representative data set for indoor like manipulation type applications of robots. So what we see here is that our method is not the best performing method. So there are some like recent state-of-the-art models which do somewhat better, not a whole lot, but definitely slightly better. But we are like competitive across the board, regardless of the object type. When we go to pose tracking, we actually outperform the state-of-the-art methods. So which shows that the fact that we used these color pair as sort of an unifying descriptors to generate our features, that definitely has some merit. And what I am particularly excited from, again, a long-term robot autonomy and deployment standpoint with low-cost commodity hardware, sensors, and everything, is that there will always be these noise and like missing frames and all. So as I told you, we ran some tests by deliberately not showing all the frames or feeding all the frames to the robot. So in fact, we skipped like 4 frames at a time, and then it gave like the robot every 5th frame, and then asked it to track the poses of the objects. And it did remarkably well. It wasn't as good if it had seen all the frames, but still, if you look at this average performance, that's better than all the bench methods that we benchmarked against. We did some ablations study to sort of identify what is actually helping the overall framework do well. And we see that kind of like, as we had conjectured, that the use of these color pair filters is like avoiding a lot of these kind of crippling errors which can happen either on your 3D translation estimation side or on the rotation side, which helps a lot when again you have these missing frames or some like noisy observations. So these kind of critical errors are what are being tackled well by our use of these color pair filters. And then last but not the least, we are very happy with the runtime performance. So everything is working on a standard Jetson AGX Orin platform. So for initial pose estimation, it's about 7 frames per second. We set out with the target that we need to exceed 5. So we do that for 5 object scenes. So now there can be more cluttered scenes. So there is still scope for improvement there, but at least on YCV type scenes, it works well. And then once the estimation is done, the post tracking is actually even faster because it can reuse a lot of the information, temporal coherence and all from the previous frames. So it is definitely like deployable on like commodity robot platforms. So that was the main target that we had initially. So here is like a quick demo of it working on a Locobot, which is a very low cost robot platform. You can see that it's there are some jitters, but it's fairly like stable in terms of the estimating and tracking the poses of these objects. Hey. Okay, so to sort of summarize, we presented this unified framework, and for texture, again, it's only going to work for textured objects to do both pose estimation and tracking. It does not require, that's again to reiterate, does not require any pose label training, and it works in real time with full onboard processing. And of course, this is kind of our first step in like robot real-time robot pose estimate, object pose estimation and tracking. Lots of scope for future work. There will be objects that the robot will be dealing with which will not satisfy our like criteria, textureless objects, reflective objects, and other challenging cases. So we need to augment our framework to deal with those scenarios. And one of the ideas that we are working on actively right now is to bring these topology-inspired work that we have shown works well for object recognition, detection recognition, to also combine that with these color pair-based post-tracking work. The other, I think, the big direction that we are looking into is what happens when the robot encounters novel objects in more open world perception scenarios. So can we like also have a version like if it does know about the objects or has like the CAD files or meshes, great, it can use it, but there will be other new objects for which those information will not be there. So then like what can the robot do? Can it like rely on some maybe query a VLM model to find some information. Maybe it can also work with like a human and get some like user responses to get some ideas on what those objects are, and then blend it with more of these sort of like structure-based formulations. So we are looking actively into those directions for the future. So thank you once again for staying with me. Questions are welcome, and feel free to reach out to me, and we have the code and everything available for use as well. Thank you again.
Fantastic. Awesome research. Pretty impressive on the results there with the Jetson. Congrats. Let's take a couple of questions. We'll batch up two questions, and this is in regards to lighting. And one of the questions is, what effect does lighting have on the tracking? And then can you walk us through a little bit why um, you modeled color pairs as triangles anchored at the origin, why this geometric relationship stays so stable across lighting changes? So we're in the lighting space.
Yeah, uh, to be honest, we have done not a completely exhaustive set of experiments to claim that we are like completely robust to all kind of lighting conditions. So for instance, we have not tested it like in scenes where it was like red light, like red ambient light, and then blue light and all. So the like our empirical validation and all has been sort of been in scenarios where it's still kind of yellowish, whitish ambient light, but with different intensities. So sometimes like bright lights, sometimes a lot more dim or moderate lights, and also the hue is also gone varied a little bit, so it's kind of bright yellow versus like dim yellow. So that's the scope of like the testing that we have done. So that's not the same as like completely changing the color of the lights altogether. So with that disclaimer being put, the origin here is actually the origin of the LAB space. So that comes from the how this Scilab space works. So we could have considered, and in fact, that's something we are doing right now, where, as I said, instead of looking at pairs of colors, we can look at triplets of colors or like other higher order combinations. But this was a good first step, which was implementable. It gave some nice results, as you could see. So the triangle actually is being formed because like we are considering from the origin of these LAB space in which these nodes are like basically projected or they are residing in. And what we are trying to capture are like these like some cosine based comparisons of these angles between these edges of the triangles, their relative values on the L axis or the luminosity axis and things like that. So that's what we have done right now. But you could imagine that like instead of just these triangles, you could get potentially more the robustness with like higher order geometric structures like quadrilaterals and others with a greater degree of interactions.
And then one final question here, and this is in regards to your tracker beats all of the baselines on fast YBC, even when you subsample to every fifth frame. This is
Right.
massive as it outperforms methods running on full dense video. What are the major reasons why there is so much headroom that you show here? I guess what's the smoking gun or the smoking guns that allowed for these results?
This was, I think, a pretty fair comparison. So we'd, I mean, did not optimize any of these benchmark methods on the fast YCV dataset. Maybe they could have done better with like some bit of fine tuning or something, but we did not do that for like our method either. So I think it's like in general, like if you look at the fast YCV data set, it's not the most noise-free kind of a data set in terms of evaluating your post-tracking methods. A lot of these other post-tracking methods, they have not been evaluated on this data set when they were actually published. A few of them were, but not all of them. They were mostly benchmarked or tested on, I would say in some ways, less noisy data sets. But this one, we believe is like very close to what robots might encounter in practice in like real deployment. So that's the reason we chose this. And I think it was just a fair comparison where like our method came out on top.
Fair enough. Awesome research. Thanks for the presentation.
Thank you so much.
All right. And a quick reminder, all the talks are being recorded. We'll try to get these uploaded as quickly as possible on Wednesday. Thanks to all our speakers for taking time out of the day to present their research. Awesome stuff. It's always good to catch up on the latest stuff going on in this space. Also, thanks for everyone that hung in there for the presentations. And don't forget, tomorrow we have our day 3, the final day of the Best of ICRA series. So we hope we shall see you there. We're going to go ahead and leave the Zoom open for another 15 seconds or so if you have any closing questions and or comments. Otherwise, hopefully we'll see you at a event soon. Thanks, everyone. See you.
Recording